Here we are with example 3, looking at our axial loading. Remember, it's just looking purely axial. We have two force members. They're either in tension or compression. And so with axial loading, we have stress equals that normal force over area. We have stress equals E times strain. We have strain equals change in length over length. And we can rewrite this then, that delta equals PL over AE. Or normal, or whatever you want to call that force. But this is for purely axial. We are just pulling or pushing, okay? We have to make sure, though, that we are in the elastic region for this to work. The load is supported by 4 304 stainless steel wires that are connected to the rigid members AB and CD. Determine the vertical displacement of the 500-pound load if the members were originally horizontal when the load was applied. Each wire has a cross-sectional area, okay? So I can go in the back of your textbook, and we can not calculate, but we can look that the modulus of elasticity is 28 times 10 to the 6th pascals. And remember, a pascal, or not pascals, hello, how about KSI? Okay, how about KSI? We are in units of feet and pounds. So we have 28 times 10 to the 6 KSI. So we have to figure out how this force is being distributed up through our system. I am given for each of these a length. I am given for each of these an E. I am given for each of these a cross-sectional area. So I'm going to have to find that internal normal force so that I can calculate the deformation, the displacement. If I'm looking here, I have a rigid body rotation, rigid body translation. If I'm looking at this 500 is much closer to this wire than this wire. And all things being the same, they have the same area and the same material. PL over AE, I'm going to have a much bigger P, and I have a much bigger L. So I'm guessing that my delta over here is going to be much bigger than my delta on this side. So it's going to kind of come down and probably rotate something like that. Now, when I'm looking over here on this side, okay, when I'm looking on this side, then I can see I'm pulling closer to DE than I am CF, and these are the exact same wires in terms of length, diameter, and material properties. So my guess is this is going to have the higher force. It's going to want to come down and kind of rotate as such, okay? So the first thing I have to do is discover my equilibrium, what forces are going where. So let's start with our free body diagrams. We are looking at equilibrium. And we have to start at the bottom. So we're going to draw our rigid bar from A to B. And I have 500 pounds going down. And I'm going to have a force in cable BG. And I'm going to have a force in cable AH. And this is 3 feet, and this is 1 feet. So I can sum moments about A and get the force here, and then I can sum moments about B and get the force here. But I also can see it's a 3 to 1 out of 4. So if I look at that, I can already tell you that the force in the force in BG is going to be, well, what's 500 divided by 4 feet? It is 125. And what is 3? So we have a 3, it's going to be 3 times bigger because we're closer, is 375. And if I look over here, the force in AH is going to be 125 pounds. But again, we can sum those moments and calculate that. Now, when I look at the next rigid bar, so we're moving up the system, I'm going to have a force in CH. That is not a CH, that's a CF. And I'm going to have a force over here, a force in DE. And I have this load pulling down because if I cut that cable, Okay, then if it's pulling up, it's got to be pulling down, and I know that this is FAH, that's what's pulling down, and we already found that that's 125 pounds. So again, I could go back, and I know that this is going to be 125 divided by 3, and then I'm going to have 2/3 here and 1/3 there. Or I could just sum moments about this point D and calculate this cable. So we are at 1 foot and 2 foot. Okay, so let's go ahead and take this around, and I have 125 times 1 negative, okay, plus this force times 3 equals 0. Move it over so we can divide this by 3, and look at that. Just like I said, the force in CF is 41.67 pounds, and then we can multiply that by 2, and the force in DE equals 83.33 pounds. Okay, so it's just ratios. It's super easy peasy. So that's my free body diagram of equilibrium. Now I need to draw a free body diagram of deformation. Okay, so we're going to look at this top bar. When I'm looking at DC, here's where I'm starting. And I can tell you it's probably going to come down, but it's probably going to come down farther here because they're the same cables, but this one has more force. So we're going to over-exaggerate this so that I have room to write. Okay, and I know that this displacement here has to come from the change in length of cable CF because there's nothing else above it. And this displacement right here has to come from the elongation of cable DE. Okay, and then this point H is just going to go along for the ride. It's going to move from H to H prime because we are just moving on down, and it's going to come at a ratio somewhere between these two, 2 and 1. Okay, so I'm going to have to figure out, and I'm just going to go ahead and set this up. I know that this little nugget right here is the change from C to F, and now I can use similar triangles. Okay, and I'm going to just call this delta prime. I don't know what else to call it right now. We're just making something up. But if this is CF, everything is coming down that amount. I know that H is coming down that amount. And now I have this beautiful little triangle. So we can actually do, this is all from delta DE. We can do similar triangles. So this piece right here, has to be delta DE, that's all the way down, minus delta CF. And then by similar triangles, we're rotating about that point. I know that, that 2 is to delta prime as 3 is to delta DE minus delta CF. Okay, and so I can cross multiply, okay, and H to H prime then is delta CE, or delta CF. I don't know why I can't see these letters. They're so tiny. Delta CF plus this little nugget of delta prime. Okay, and as it's going down, that means this cable is going down, okay, but this cable is also stretching. This cable is also stretching. So the displacement of A is going to come from delta H to H prime because of what's going on above it, plus the stretch in this cable. So let's look at this bar right here, and we'll get there. So here's this bar down here on the bottom, and we are applying this 500 pounds right there. And this is 1 foot, and this is 3 feet, okay? And we've already discerned PL is going to make this stretch a whole lot more. So it's going to kind of be wonky this way. Okay. And this cable change, how is A moving down? A is moving down because we already moved H to H prime. So that's going to be delta H to H prime plus we now have the change in length from A to H. Okay. You guys seeing all of this? This delta is because we are increasing cable B to G, And I want to find ultimately how far down does this load move? How far down do we go from I to I prime? And we're going to do the same thing. Okay, we're going to do the same thing here where we know everything is moving down this much. And then this piece right here is delta BG minus this nonsense. Okay, and then we can use similar triangles to find delta prime prime. And I know ultimately that the displacement from I to I prime is delta HH to H prime plus the elongation of that cable plus delta prime prime, which is the little extra bit that we come down over here. So that sounds really confusing, and it took me a long time to explain, but if you can draw this out, deltas are easy. They're just PL over AE. They're just PL over AE. So here's my game plan. I found internal forces. I've now found the relationship of deformation. I have my similar triangles taken up. So now it's just a matter of finding deltas. Again, we should always check to make sure we're within the elastic region. So that means for each cable, I need to make sure the stress in the cable is less than the yield stress of the material. Okay, and it is. So we're just going to keep moving forwards, but you would need to check that because otherwise you have to use a stress strain curve and you can't use the small deformation that you get in the elastic region. So let's start over here, cable CF. So delta CF equals the normal force in CF, the length of CF, the area of CF, and the E of CF. The normal force in CF is 41.67 pounds. The length of CF is 3 feet. The cross-sectional area is given at 0.025 inches squared. Oh, what do I got to do here? 12 inches per foot. So we might as well go back. That's 36 inches. Okay, this is 60 inches. 1.8, 12 times. We have 21.6 inches here. Okay. E, 28 times 10 to the 6th KSI. So let's multiply this out. I get 41.67. Oh, this is in kips. Okay. This is in pounds. This is in kips. This is in pounds. Is that right? Let me look in the back of the book one more time. Okay, this is where it's always, you got to check those units, check those units, check those units. 304 stainless steel in the KSI, 304 stainless steel right here coming across, modulus of elasticity, 28 times, 10 to the 3rd KSI. That's where it is. So it's 10 to the 3rd KSI, which means 10 to the 6th is in PSI. See how important it is to check your units? Otherwise, you're going to be off by factors of ginormous amounts. So we're pounds, inches, pound per inch squared. Perfect. 41.67 times 3 times 12 divided by 0.025, 28 e to the 6th divided by, and I get a delta of CF of, okay, 2.14 times 10 to the negative 3. So that would be 1, 2, 3. 0.002143 inches going down. Now I'm going to find delta of E to D. So I have that internal normal, which over here it's 83.3 times the length of 36 divided by 0.025 divided by 28 times 10 to the 6th PSI. And, you know, it should be twice that because we have twice the load. So we get boink, boink, 0.04286 0.04 inches. Okay, so now we can come back here to this. We can come back here, and I know that CF is 0.002143, and I know that DE is 0.004286, okay? And really, I know that this is a third, it's a 2 to 3 ratio, so this whole amount has to be somewhere between these two, but I'm just showing you how to do it with similar triangles. So that means this little piece right here is 0.002143. So I need to find the height of the triangle now. And that's going to be the whole amount over here of 0.004286, okay, minus that. So we have a height of our triangle of 0.00214, okay? And so now I can say, well, 2 is to delta prime, the little piece of this triangle, as 3 all the way over is to the height of this. So I'm going to go ahead and erase that. Okay, I'm going to go ahead and erase that. Actually, I'm going to leave that there. It was delta DE minus delta CF. We'll just go over here and do it. So I have 2 is to delta prime as 3 is to, okay, is to 0.004 minus 0.002, so we get 0.002143 inches. So now we're going to do some cross multiplication. 2 times 3 divided by, and I get that delta prime is 0.0014286, okay, inches. But that's only a piece of it. I have to go back and add that to plus delta CF, okay, to get the total displacement of H to H prime. So 0.002143 plus. So the displacement of H to H prime equals, this is a big step in our game, equals 0.00357 inches. Okay? So that's how far point H is coming down because of what's above it. Now point A is going to also come down that 0.00357, plus it's going to have the stretch there. Okay? Remember, it's H to H prime plus the stretch. So now we have to go back and figure out what is the stretch of cable AH. Okay, and that's going to equal the normal, the length, the area, the modulus of elasticity. So what is our force in AH? Okay, can you go back and look? 125 pounds. So I have 125. Okay, its length is 21.6 inches. Divided by, its cross section is also 0.025. And it also has the same modulus of 28 times 10 to the 6th PSI. 28 times 10 to the 6th PSI. So everything's in pounds. Okay, everything's in inches. Everything's in inches squared. So let's calculate that out. And I'm leaving this in because that's the displacement that we had before we stretched the cable. So 125 enter, 21.6 times 0.025 divided by 28e to the 6th divided by, and I get this nice displacement of 0.038. There's a lot more zeros in there, aren't there, friends? 0.003857 inches down. So if I want the total displacement of A to A prime, okay, so if I want the displacement of A to A prime, I know that it's the displacement of H to H prime plus the elongation of that cable AH. So when I add H to H prime plus this cable coming down, okay, plus this cable coming down, I get a total displacement down of A to A prime of 0.00743 inches. Okay, and we are still not done, friends. That is this value here. That is this value here. I still have to find the elongation of cable BG so that I can go back and look at what is going on right here with my similar triangles and find the displacement of, okay, remember what do we want? We want the displacement of the load. Okay, so I have that. Now I need to find the displacement of B to B prime, which is the elongation of cable BG. So I need the force in BG, which is 375 pounds. The original length is 60 inches. The original area is 0.025. And its modulus is 28 times 10 to the 6th. When I calculate that out, so we're going to leave this in here because I know that's this part of my triangle over here. I have 375 enter, 60 times 0.025 divided by, and then I have 28 e to the 6th divided by. Oh, it's actually it's a bigger number because it's to the -2, so it's a bigger number. So I get that the elongation of cable BG is 0.032143 inches. So on this side, it's 0.007. On this side, it's 0.032. Okay, it's 0.032. So when I'm looking at the similar triangles, okay, this is 0.037, and everything is going down. Sorry, let me move that up. Here it is. Everything is going down 0.037. Okay, the A is moving down from A to A prime. The load is moving down, okay, from I to part of an I prime, and cable BG is stretching this amount. Cable BG is actually elongating all of this. So if I'm using similar triangles, then this value for my triangular section is 0.032 minus 0.00743. Okay, you see that? So we have 0.032 minus, I'm going to swap these and I'm going to subtract, and we're going to erase that now that we've gotten this sorted out. And this is 0.024714. So now I can use similar triangles. Okay, we're back to similar triangles where we have 0.0474 is to 4 feet, as this delta prime prime is to 3 feet. So this is to 4 feet. Okay, that's what we had, as this is to 3 feet. Okay, so let me find the back of another piece of paper so we can keep on rolling. Keep on rolling. And this is a really good example of what you might find on an exam. Okay, so here we have it. Make this bigger. If this is 0.00743, then this has to be 0.00743. And this value here is 0.032143 minus 0.00743. And we're trying to find ultimately the displacement of our load. This is a 1 and a 3, so the whole distance here is 4. So I have 0.032143 minus 0.00743 is to 4, as, okay, as delta prime prime is to 3. And then ultimately we're going to find that the displacement, now I can move this piece of paper, of I to I prime, which is the load, is going to equal 0.00743 plus delta prime prime. So let's calculate delta prime prime. Okay, delta prime prime. So I already found that this minus this was 2.471 times 10 to the -2. So we're going to divide by 4, and then we're going to multiply by 3. So I get that delta prime prime is 1.853 times 10 to the negative 2, which is 0.0185336, which is a 4. So we can now come here, scratch that out, and I have 0.01854. We're going to add that to, okay, the top part of that, 0.00743 plus. And I get that the delta from I to I prime after loading is 0.02327 inches down. Okay, what does that mean? What does that mean? Let's go back through our mess here. What does that mean? It means as I loaded this system, this is going to drop down because I'm stretching these cables, so it's going to come wonky down. We're applying a force here, so these are also coming down. So when I load this, this point I is going to go down 0.02327 inches, which is very small. We wouldn't be able to notice it. It's very small strains. Okay, this is a very good example of an exam question, except we might have springs in here and some shear blocks, so we can have you working with shear as well.